Okay, welcome everyone to this live session. This is the live session for the course Measure Theoretic Probability 1. This is a 8 weeks course on this topic which explores the mathematical foundation of probability through what we call as the measure theory. So to start off with, I'll just quickly give a brief overview of the topics that has been covered in the first 4 weeks, and then we will take up questions. So some questions have already been submitted over the Google Forms response sheet, and if you are joining in, you can also post your questions through the YouTube chat box as well as the Zoom, whichever is convenient for you. So we will take them up one by one. All right. So I'll start off with a quick overview of the course contents that are available on the NPTEL portal. So in the first week, we started looking at the basic structure of the information that is available through a random experiment. So towards that direction, we started by looking at the sample space, which is the list of all possible outcomes. Then we focused our attention to special subsets, which led us to this notion of events. And then we look at these collections of events and we explore their structure. So towards that direction, we spend some time on looking at the structures of field, sigma field, monotone class, and others. And after that, we went to the structure of the special type of sigma fields involving the Borel sigma field, specifically the Borel sigma field on the real line. After that, the main content shifted to the focus on the measure. So this we started looking at in the second week. So the measure is essentially trying to understand what is the physical significance or the area or the size of certain sets. So that is the way to look at it. So we studied properties of measures, and then the wider information that we collect from a random experiment was reformulated into a triple, basically the sample space, the sigma field of events, and the underlying probability measure. So we end up with a triple, which we call as a probability space. So we studied their properties, and then we moved on in the next week to looking at the structure of random variables. And here we encountered this concept of measurable functions, which is a more broader concept. And here we studied the algebraic properties and some analytical properties of these measurable functions. And in the fourth week, we combined everything together. So we have a probability space, we have a random variable defined on it. So how do you link the random variable on this space and the underlying probability measure is that if you link them together, you end up with the law of the random variable, which turns out to be a probability measure on the real line. So that's how the main connection came in, and then we started studying the properties of the law that now is getting induced towards the real line side, the range side. And we said that the entire information about random variables is essentially getting captured through the law because you are essentially interested in probabilities of the random variable taking values in a certain range or a certain set. That's exactly getting captured by the underlying probability law. And then we connected this notion to the distribution function of the random variable. Basically, the idea was that if you have the distribution function, in principle, the underlying probability law on the real line gets uniquely determined. So we started looking at properties of the distribution function. So essentially, the idea is either you analyze the random variable through its law, which essentially talks about the probability of the random variable taking values in a certain list of subsets. But alternatively, you could also choose to look at the distribution function, which essentially carries the same information. So these are the material that has been covered in the first 4 weeks. And then in the subsequent weeks, we will study some more further advanced topics. So these are the main topics that has been covered so far. And now I will move on to taking up the questions that has been submitted over the Google Forms. So So there was these questions. So I'll take it up one by one. So the first question, I'll read it out for you. It says that for the Bodel sigma field on the real line, we say it is generated by open intervals. Why do we specifically start with open intervals? Could we not also take closed intervals or some other sets and we still get the same sigma field? Okay, so the couple of clarifications. We define the Bodel sigma field on the real line as generated by open sets and not open intervals. So this is an important distinction. We are saying that we'll start off with the open sets on the real line and then generate a sigma field out of it, which we call as the Bodel sigma field on the real line. So that's the definition. Now later on we show that this same sigma field is getting generated by the collection of open intervals or closed intervals, and there are some list of sets that we had considered, all of which generate the same sigma field. So you could have as well defined the Bodel sigma field on the real line through any other such collections. However, what actually happens that this notion of Bodel sigma field, that is not really specific to the real line. You can actually generalize this concept of Bodel sigma field to much more general spaces. So in fact, we already have discussed the Bodel sigma field notions on RD, which will also be required later on when we talk about random vectors and all. But the main point here is that you first have to understand what is the list of open sets, which is through which we are defining the Bodel sigma field. You see that if you have the collection of open sets on any general space, which typically is called a topological space. So there is a general notion of topology on a set, which exactly gives us the notion of open sets. And topology is the collection of that open list of open sets. So we are connecting to that more broad general notion. And from that idea of topology, then you can define a sigma field. And therefore, in very general setting, wherever you can talk about open sets, you can talk about the collection of all open sets, you can then define a Bodel sigma field. So that is why the definition of Bodel sigma field on the real line is the start is through the open sets in R, because you are actually connecting to a more broad definition of a Bodel sigma field on any general space where you can talk about open sets. So this is much easier to generalize. But then for the special case of the Bodel sigma field, of course, I agree that you could have as well taken open intervals or the list of closed intervals or any other special collections that we have already discussed. And note that all these various types of sets are automatically included in the Bodel sigma field on the real line. So these are all the information that we automatically get about the structure that is inherent within the Bodel sigma field on the real line. So hope this clarified this question. So I'll move on to the next one. When we define a random variable as a measurable function, it feels quite abstract. Could you share an example that makes it clear why measurability is such a necessary condition? You see, the main notion that we are interested in is about random variables and the events corresponding to a random variable. And finally, we would like to know about the probability that the random variable takes values in a certain range. Now, most often, let's say I am interested in the situation that my random variable takes value less or equal to some small x. That's exactly the event that my random variable capital X is less equal to small x. Now you can visualize this as we have discussed in the course. You can visualize it as the inverse image of or the pre-image of the interval minus infinity to x closed. So if you treat the random variable as a function from the sample space omega to the real line, then on the real line side, you look at the interval minus infinity to closed small x and look at the pre-image. That's exactly the image or that's exactly the event that you are interested in when you are dealing with a random variable. So therefore, it's therefore very much important whenever you are dealing with a random variable that you try to understand this structure of the pre-images, which are going to give you these events on the domain side. And that's exactly are the special types of events that connect information about your underlying random variable. So that's exactly the notion of measurability. And you would really like to talk about the measures of those type of sets or the probability of those type of events. And that's is the structure available on the domain side, that you have the sample space, you have the sigma field containing the special events, and you can talk about the probability of all those events. So that structure is already available to you on your domain side. You are now taking advantage of this measurability condition to pull back that information to the domain side where you can talk about the probability. This is why you need to have this measurability structure for the random variable, that you can talk about the random variable taking values in a certain range or in a certain set, and that's exactly the pre-image of that set that you are talking about. And that's exactly is the condition required because you would like to bring that event specifically on the domain side and talk about the probability of that. This is why the condition about the underlying measurability structure is very much important. So hope this clarified that question. So I'll move on to the next question. So it says the characteristic extension theorem looks very technical. Could you explain in simple terms why the uniqueness part is so important in probability? You see, we have spent some time in the lectures while talking about the application of this general theorem, which is the characteristic extension theorem, but specifically to probability measures on the real line. So what we said is that after doing a certain amount of arguments and application of this characteristic extension theorem, you can bring it down to this very specific information, that what is the structure of a probability on only these type of sets which are minus infinity to x closed. So I look at this type of intervals minus infinity to small x closed as I vary my x over the real line. So I get various types of such intervals, and I am interested in the probability of that. So if you just know these information, instead of knowing the measures of all possible sets, you just know this information. You can rebuild the measure in principle, which the characteristic extension theorem is allowing you to do. So this is the application of characteristic extension theorem, but what is the upshot then? The upshot is, instead of knowing the probability of all the Borel sets, you just know the partial information, which is the probability of all these intervals type sets, only that. Once you have that, that exactly connects to the distribution function of the measure, the probability measure. So if it therefore says that distribution function is uniquely identifying the probability measure on the real line. So therefore, instead of knowing the entire measure on the real line, you just need to know the distribution function. So that is the upshot that is coming in through the application of the characteristic extension theorem. But now note that the special case of these probability measures that we are looking at are the probability measures which are corresponding to random variables, right? And for any probability measure, you can construct random variables. So that's essentially the entire class. So if you are interested in the probability law of a random variable, you really need to know the underlying distribution function. So in basic probability theory, what you do is that you understand the law starting with the distribution function, but here we are making that notion much more concrete. We are justifying that yes, you actually need to do that because of the characteristic extension theorem, that if you need to study a general random variable, you need to understand its law. And its law, now we have defined it as a probability measure on the real line. And to, instead of trying to understand everything about the law, you could just as well understand the distribution function. So this is what the characteristic extension theorem is allowing you to do. So it's very technical, I agree, but we have to understand what is the application. And the application is towards this very specific result, that the underlying random variable, if you want to understand it, you just have to understand the underlying distribution function. So that is why the characteristic extension theorem is so much important. And that's exactly connecting to the uniqueness part also, that the distribution function is uniquely identifying the underlying probability law of the random variable. All right, so I hope that clarified that question. So these were all the questions that were submitted through the Google Forms. So I will check the the Zoom chat box first. So no questions so far. And I am also checking the YouTube chat box. So no questions so far. So if anybody has joined into the live session, I would request them to post their question in the YouTube chat box or the Zoom chat box, either one, whichever is convenient. And if you have a question, please feel free to post it. If you have a comment, please also feel free to post it. So we'll wait a short while in case you have a question or a comment. Okay, so no further questions has come in the Zoom or as well as the YouTube chat box. So we can close the session now and thank you. So in case you have any further doubts, please make use of the Google forum that was associated to the course and post your questions there. I would be happy to take up the questions there again. Okay, so we can stop here. Thank you.
Thank you so much, sir.